Good evening, everyone, and warm welcome to all the participants of the DeepTech Hackathon. On the behalf of DeepTech Hackathon team, India Electronics and Semiconductor Association (IESA), Next Semiconductors, and I4C Interregulative Innovation Center. As Saurabh Bhuvari, I'm delighted to welcome you all for today's knowledge session as a part of DeepTech Hackathon. And the topic for today's session is AI on the Edge, deploying TinyML on microcontrollers. And we are privileged to have the expert from NXP Semiconductor, Mr. Arjun Bande sir, as the speaker. And again, welcome you again, sir. Thank you for joining. And again, I'll give you an introduction. So, Arjun sir is Director Design Enablement, AI Digital Transformation at NXP Semiconductors. He is a seasoned leader in the semiconductor industry with over 30 years of experience across R&D system integration, project management, and technical sales and customer enablement. As a director of design enablement at NXP Semiconductors, he drives digital transformation in VLSI design, leveraging AI and automation to accelerate design cycles and enhance collateral quality of the quality for the advanced technology nodes, serving automotive, industrial, and IoT markets. So also prior to that, he spent more than a decade in Siemens EDM, leading high performance team, strengthening technology partnerships, and advancing VLSI design methodologies. So he began his career at Kirloskar Electric, developing industrial and power plant systems, and he holds a BTech in electronics and telecommunication and MTech in AI. Welcome you also. Thank you for joining. Um, Before that, so today's topic is quite interesting on the age. I'd like to just share one thing that today I'm actually conducting a hackathon on AI for logistics. Quite similar. So we can see like how the AI is revolving on over the industry right now. And today we'll be talking about AI for age, like how AI is going to take over semiconductor industries. Quite interesting. Um, and also we know that recently the budget in budget, we are starting with semiconductor mission phase two, which is quite exciting, and budget allocated is almost 76,000 crores. So we can see like how this industry gonna increase and how India gonna be in the top four, building the semiconductor, getting into the semiconductor sector, getting into the product nation. So this is, I like to say, and this is a very good opportunity for all of us as to build solutions related to this industry where we can, like, India becomes top uh, nations producing the semiconductors, developing solo chips in the semiconductor chip design or the concepts or topics related to it. And so with this, I I without further delay, I would like to request Mr. Malikarjun sir to begin the session. Over to you, sir.
Thank you, Saurabh, for a good intro and keeping current with the uh, current happenings. Thanks for that. Okay, so let me share my screen. Can you please confirm if my screen is visible and am I audible?
Yes, yes.
Yes, sir,
Okay.
absolutely. Sir. Screen is visible and you're audible, sir.
Okay, thanks. Okay, let's get started. Hello, my dear students, and some participants from industry also have registered, is what my understanding is. So this is the second webinar in our this hackathon journey. The hackathon is about defect classification or semiconductor defect classification system on AML or edge implementation using AML. So first webinar we did about, we spoke about the defects, why these defects are caused, what is the impact of these defects, and how do we classify them, using some AML methods. We covered those topics in the previous webinar. In today's webinar, we will be talking about what are the requirements, what are the challenges when we want to deploy these systems on, or the AML systems on edge devices. So with that, the agenda is going to be cloud versus edge computing, and what are the edge computing requirements. And we will briefly talk about what are the microcontrollers, what do they have in it, why they are important. And we will also then talk about NXP specific MCU portfolio. And specifically, we will talk about RT1170 device, some requirements, some features, and some requirements to implement on this, and what software platforms are required, followed by question answers. So this webinar, the generalization or general topic or topics for you, not just for this webinar, not just for this hackathon, but it is if you're an electronics or computer science student or electrical and electronics student, you need to know the big picture of this electronics industry, particularly the microcontrollers, the hardware that is required to run any application, because these devices are going to be there everywhere. They're already there everywhere, but then their population is going to increase more and more. So we will understand from that perspective edge computing and cloud computing differences and so on. That is in the generic view. And then specific to the hackathon, you will learn some things which are required to be known, and you need to take care of these things for this hackathon. And within that hackathon, so whatever we speak here is going to be very important for phase 2 and phase 3, where you must know these things. But phase 1, a portion of this is required to be known, so which we will talk more details during the presentation. Okay, so many of you heard of these words, cloud computing and edge computing. So what is the primary thing that is happening over there? So the cloud concept started almost, I think, 10, 20 years ago. Now, many people were wondering what is this cloud and so on. And it's all about computing at a remote location with a huge compute capability. That is your cloud. And all the computations, most of the computations typically happen in those remote servers. Nowadays, earlier they were called as servers. Nowadays, you can call them as data centers, particularly in the context of AI. So if you talk about your ChatGPT, for example, this lot of computations and inference is happening at the cloud. And versus some of the IoT devices, many of them you see, even you could think of your smartwatch, or you could think of your home automation, or some of the medical handheld devices, or some of these payment devices, some of these other systems like things in automotive, where the computations has to happen locally over here for many reasons, which we will talk in a moment. So these computations, some part can be pushed to cloud, some part will have to happen on the device where the device is kept. The reason for that is, for example, you are driving an autonomous car and with a lot of intelligence in it. And if a car detects an object and it has to determine what object that is, think of that object captured and sent to a cloud and computations done over there, inference done over there, then the data coming back to the car, oh, it is a human. By that time, the car would have gone past that phase, gone past the traffic signal, or gone past the vehicle. So for those kind of applications, you need the computations have to happen locally here. That is called edge computing. There could be a mix of these two things, edge computing and cloud computing, wherein the immediate requirements can be addressed at the edge level within the car or within your smartphone, within your watch, or within your home appliances. And one other important thing is the factory automation. There are a lot of robotics over there where the edge computing is very, very key. And After all these immediate requirements are met by edge computing locally here, some data may have to go to cloud. For example, the vehicle statistics, how long the car has been in use and how it has been driven, where and all it traveled, and what all the kind of collisions it had happened. All that data you may want to consolidate and do some data analytics on that. That you don't need to do it inside the car. That can go to cloud or the data center or the server and get uh, computed over there. For example, you're running a shop or a factory or in a mall where there is a super store uh, where you want to collect a lot of customer data, their buying habits, and do a customer analysis or do a sales analysis or do a factory production output analysis. These kind of things you don't need to do instantly on the edge. So these computations can go to cloud and you can do a lot of data analytics over there. So these are the three forms of computations in today's requirements: cloud computing, edge computing, and a mixed computing. So I have listed over here on the left-hand side. So what are the requirements for those things? Um, Cloud computing trains large AI models, which we spoke about. You can keep those things both like ChatGPT, train and inference, both can happen in cloud. And of course, they will have very huge computation capacity. And they also require a lot of data to be stored over there to do that data analysis and training and things like that. And they can typically have GPUs, very huge compute, CPUs or GPUs, basically processing units it can have. And we spoke about what the purpose the cloud computation can be used. And versus edge computing, we spoke about this edge computing happens on the local devices. And we spoke about latency requirements. The moment you detect an object, you need to define, so you need to decide what is that object, what is the impact of that, what should I do? So that latency has to be very, very small. Within milliseconds, you need to be able to make a decision what that object is when you're driving a car, for example. And also, you don't want to have a lot of connectivity with cloud because all this can happen locally over here. And you don't want to consume a lot of bandwidth every time you connect into cloud. And that is going to be adding additional cost and latency. And we spoke about autonomous drives, factory robots, smart cameras, typically are the examples for your edge computing. Now, what are the requirements and challenges of edge computing? So we spoke about real-time, deterministic. And another important thing is ultra-low power or long battery life is required. So you mount a camera or a TV camera on in front of your house, and if it is battery operated, or you are carrying an intelligent earphone, for example. So these are all battery operated devices. So you need to have a very long battery life. So power requirements you need to keep in consideration. And the local intelligence, you need to be able to compute in this small device, a lot of computation. So you need to be smart enough to decide what kind of computations I should do locally, what kind of computations I should send it to cloud, and so on. And another important thing is security of these systems. What if somebody just snatches this device and takes it away? It has a lot of your personal information. Or even if it is with you, what if somebody intrudes and injects or steals your data? How do you arrest that? How do you maintain the device high security? Another huge requirement for edge computing. And cost. So where these devices are deployed, so in your home, you may want to have about 4, 5, 10 different edge devices. They have to be cost effective. So these are your requirements for edge computing. Now, how this edge computing is done? So you basically have a small device called microcontrollers. Typically, you can name them as microcontroller-based devices. And these microcontrollers have a lot of very good features and advantages, but they have a lot of constraints also. So first of all, let's quickly look at what is inside a microcontroller. So a microcontroller typically has a processing unit because it need to do some computations. And then it will need to have, you can think of it as a small, very tiny computer. So it need to have a RAM for quick operations. It need to have a flash for storage, and then it need to have the connectivity. So it wants to communicate to external world. Also, it want to both to external and from external world. It should be able to communicate. So for which you require interfaces. It could be a wired interfaces or wireless interfaces. Wired interfaces directly connecting the wire through USBs and things like that. Wireless interfaces like Bluetooth and your Wi-Fi. So it can have those kind of things. And peripherals. So peripherals, what are these peripheral blocks? For example, you may want to do an audio processing. You may need an audio A to D converter and D to A converter. You may need motor controllers. You may need some timers on that. And you need specific I/O interfaces. So these are all going to be your peripherals. So these are all packed together and configured optimally inside a microcontroller. So this is like a tiny computer which has all the qualities of computer, but very specialized, and it can do only limited things because we want to meet those requirements that we spoke about. And I have listed the challenges with microcontrollers: limited RAM and flash, both the random access memory for dynamic computations or for static storage like flash. They will have a limited size because you want to meet all those requirements, power, cost, and things like that. And modest CPU performance. Even CPU, you cannot have put some very big CPU which can do millions of operations per second. You don't require those kind of things because that will come with cost and also the power hungry they are. So you need to optimize the CPU. Those compute capacity will be very limited. And we spoke about power limitations and the reliability concerns. So these devices will have to, they may not have most of the times an air-conditioned environment in factories or even in home, or even if it is mounted on the street, cameras and things like that. They will have to be reliable to work in these kind of environments. And we spoke about security. So they need to be able to provide the security, which you cannot put some heavy algorithms and make the CPU run this algorithm to check the data every time, whether it is secure or not, some breach has happened or not. So those requirements are very limited. Those features will be very limited in microcontrollers. And of course, cost we spoke about. So on one side, you have the requirements for edge devices. We need to do these things. At the same time, to implement them, you have limitations with microcontrollers. So how do you balance these two things is the art of designing your microcontrollers as well as edge systems as well the AML systems. Next, can someone confirm me? Is visuals and audio is okay so far?
Yes, sir.
Clear?
Yeah.
Thank you. Now, gone are those days where these microcontrollers are, I wouldn't say dumb devices. They are not intelligent devices. For example, a motor controller. Just need to monitor the speed of the motor. You need to ensure the voltage fluctuations are not there. It needs to see the load on the motor, and then it will have to just keep firing the pulses so that the motor maintains its constant speed or some variable speed, whatever based on your application. It need to do that. And over there is nothing like inference. It is almost a hardwired feedback loop. It works. But nowadays, every system is becoming intelligent. For example, when you mount a camera on your door, so it can be a face detection, face recognition, AML application can be deployed on that. So it can see if it is a known face, it can unlock the door. If it's an unknown face, it can restrict the access. So the small device is now an intelligent device. So even your car number plate detection and then opening the doors or opening the toll gates and things like that. And your AI systems wherein it can differentiate between an required sound, that is the human speaking to you or some music you are listening, versus the background noise, a train passing or some other noise due to airflow and all. So you should be able to differentiate again. So you need a mix of hardware and intelligent classifications over there and separations over there. So these are all getting intelligent. Now, to how do we build intelligent systems to be able to deploy on these tiny devices? So some of the requirements are the design considerations. So these are, again, I told you about 70% of this is very much required for you from a generic understanding perspective. Tomorrow, all the students, when they go for interviews, when they get into companies, when they look at what am I going to design, what are my key challenges, from that angle, this is going to be very, very useful, a very generic webinar, and 30% related to hackathon. So what are your design considerations? Keep the model small enough to fit. So this is one of the primary requirements. See, most of you have built by second or third semester, you are already talking about building AML systems and all. You have abundant resources when the initial thoughts are coming into your mind. You have no restrictions on memory. You have no restrictions on how big the data sets would be and all. Because you put it on Kaggle or you put it on your laptop, or you buy the uh, laptops with the GPU facility, and you can train them, run them, inference. Oh, I'm getting these wonderful results and things like that. Fine. But the moment you think of deploying them onto AML, onto the edge devices, all these requirements come into picture. Keep the model small enough to fit. Why? Because the microcontroller on which it is going to go into, it has very limited memory capacity, both RAM and flash. Make sure AI prediction happens fast enough. So these are your challenges. The memory should be small, implementation should be small to fit into a memory. At the same time, the prediction has to be faster. As I told you, you detect in a moving vehicle, you detect an object, the prediction has to be fast to take a decision whether you have to gone past that, if it is just some garbage lying on the road, or somebody lying on the road, a drunk man, or you have to make those decisions fast. So your inference has to be fast. And these devices have to run for a long time, medical devices, some handheld devices, some house mounted devices. So you need to have power considerations. So you may be wondering, okay, people have been designing MCUs and processors for very long. What is there to design further? So today we are struggling to further optimize my clock. I can put the clock 1 gigahertz, but it's also going to eat power like anything. It will drain your battery in no time. So how do I control that clock? How do I make maximum computations or minimum required computations with the minimum clock speed and with minimum power requirements? So power is going to be a major consideration, and handle sensor data efficiently. In this case, you're taking image. You need to have define an appropriate size for the image. Okay, you put something like I don't know, 10241 by 1024 pixel image for defect classification. It's huge. Where are you going to fit that into your small memory and microcontroller? So you need to select an appropriate size of the image in this case, for example. Similarly, other sensor data, when you build AI systems for other applications, you need to know from the sensor data, how much should I sample? Some of you understand what I mean by sample. When an analog data is coming, you need to know what is the sampling frequency to meet the Nyquist criteria as well, not to lose the data, not to oversample it and all. So you need to have that kind of knowledge and intelligence. That's what, as a designer, you are going to do in these companies. Protect the device. Think of security requirements. How am I going to secure my device? That's another huge topic, which is important consideration here. And decide what runs on the device and what goes to the cloud. We spoke about this. So immediate computations, immediate intelligence required. Do that locally here. And the back office, like bank closes for transactions at 2 o'clock or 3 o'clock or 4 o'clock, right? But still after that, the servers run. They run a lot of statistics and analytics on that. That is back office. So those kind of things you send it to cloud. Ensure the device stays reliable. So we spoke about this. It has to work in harsh conditions. When you actually become a designer of microcontrollers and think of some foundry process requirements and things like that, we are looking at, oh, can it work at very cold temperatures, -40? We can go up to auto grade, we can go up to 150. So if the smart device is inside the car engine compartment, it need to tolerate up to 120, 150 degrees centigrade, auto grade we're talking about. And with that, the devices have to run for a long time. If you buy a car, if it comes for repair and some device doesn't work within 1-2 years, you see what is going to be your situation, the company's situation, right? We're looking at guaranteeing this device operation for minimum of 10 to 15 years. So devices are reliable and choose the hardware that is powerful. So basically you need to optimize what there should be the speed, what should be the power consumption, what should be safety, security. You need to optimize these devices. Those are the requirements for design considerations. So we have covered quite an amount of content within the previous slides. We spoke about many topics. Now let us have a quick intro of NXP. So NXP is at the core of these technologies, building systems for enabling intelligent IoT devices and edge devices and so on. NXP is a Dutch public Dutch company with headquarters in Eindhoven and having design and sales and support centers and manufacturing houses in many, many countries all over the world. We have about 33,000 employees, 33,000 plus employees. They're split into all manufacturing units, design, sales, and support, and all of that. So we have over 60 plus years of industry experience. So basically, it is Philips and Motorola, the parent companies of NXP and Freescale, which were merged in 2015 to become a single company. And about 10,000 or 9,500 patents held by NXP. And we are present in about 30 plus countries. And our annual revenue is about $12.5 billion. The recent numbers is what is shown over here. That's the background of NXP. And what we build cutting edge technologies for these intelligent applications. So the core areas, we're talking of automotive and industrial and IoT. In the automotive, we're talking of software-defined vehicles. Some of you know what a software-defined vehicle is. The same car you get, your friend get, but that has different features, different way behavior, different power, and different safety things versus what you have. This is just configurable by changing the software. Engine performance is configurable by changing the software, something like software-defined vehicles. And vehicle electrification, you see a lot of electric cars today, so a lot of battery charging systems and all. So you need a lot of electronics for that. So we build those things and ADAS and so on in automotive. When it comes to industrial, so we're talking factory automation, healthcare, and home automation and power energy controlling systems and things like that. These are the core areas where NXP builds systems for. And in any system, so what are the 3 or 4 primary things, tasks that you need to do? Any task you want to do, first sense. And whatever you sense, think, what did I sense? What should I do? And process it, and then connect it, and then act, take the action. So this is what our theme is: sense, think, connect, and act. So for each one of these areas, like sense, so I want to sense the in the automotive or in my car, I want to sense what is the object in the front. So we build a lot of radar systems for that, radar-based images and object detections, and a few more in those lines. So I'm just mentioning a few things over here. That is the sense part of it. And think is basically processing. So we have various types of various classes of the electronic systems, particularly the microcontrollers over here. Some of them are very, very huge. So they can control your entire car and connect different systems over there and perform different tasks like engine control, body control, and then customer safety, the passenger safety, and engine controls and things like that. So the entire car can be controlled. So we build systems, very big systems for those kind of applications. And there's an intermediate layer, which is for typically IoT edge devices, and then the low-end layer, which is typically for very, very specialized motor control applications, for example, and so on. So there are different families of microcontrollers that we build and connect. So these are the different technologies like Bluetooth and Wi-Fi and Zigbee and RAIN RFID and 5G. So a lot of connectivity are built into the systems. We enable them. And then the power management and some high voltage battery charging and battery management and high speed interfaces is all what we built. So getting more deeper into it, so I just spoke about various classes of these microcontrollers. On the left hand side over here on the graph, let me enable enter. Okay, so over here you see the low-end microcontrollers. I told you very, very specific tiny applications for which you have very low cost and low power, but very customized application-based microcontrollers. We have them. And on the right-hand side, we already spoke about ES32X series for fully controlling the car electronics and the car systems. That's on the other side. In between, we call them crossover MCUs. Crossover MCUs are something above the low end, something below the upper end. So these are the ideal sweet spot devices for implementing your AML applications. These are the edge computing, ideal for edge computing devices with intelligence. So now some of the things that I'm specifically talking about here, these in the last webinar, we had questions from some of the participants, so we are not clear about the hardware, what to look at and all. So in the webinar, sorry, in the hackathon, we mentioned in the first kickoff session about keep i.mx RT series of devices in mind. So our final exercise or the phase 3 implementation is going to be any implementation of i.mx RT series. So this is a platform, real-time platform, microcontrollers. They have different families. That's why we are specifically showing this part. What we speak here is useful for your phase 3 of implementation, in addition to generic information over here about microcontrollers. So I have i.mx RT10, RT11, and RT3 three-digit series. So within this family, you have again the low end, middle end, and the high end. What we're talking here is I have highlighted i.mx RT1170. So we would suggest all the participants here look at this device, and you can search on the web, NXP web, for details about this device. So we would suggest target this particular thing to avoid any confusion, because we have quite a few devices within the RT family. I think about 15, 20 devices. So you may be confused, one looking here, one looking here and all. Instead, I'm specifically pointing here, look at i.mx RT1170, though this is not the latest offering from NXP, but as I told you, many of these devices go for automotive applications also. The lifespan is typically 10 to 15 years. So this device is, I think, 3 or 4 years old, but it's very much active and then very much used in the industry. So you have the high-end i.mx RT3 series like i.mx RT8 and RT9 and i.mx 8 and 9 and so on. You could look at them also. They are the better and advanced devices and more capability with manageable power. But i.mx RT1170, what is highlighted here, should be the one you could look at. And we spoke about, you can see slide number 4. I just flipped back. So inside a microcontroller, what is there? We briefly discussed here, like RAM, CPUs, and peripherals and things like that. But actually, if you look at now this slide number 10, this is the block diagram of RT1170. So you could see it has dual processors, ARM Cortex-M7 CPU and ARM Cortex-M4 CPU here. And then we have a lot of peripherals like PLL, CDMA, watchdog timer, and GP timer, and plenty of other things over here. We have 2 MB SRAM. So please note, this is 2 MB SRAM. Some of you may be wondering, so I don't know, some of you, well, sometimes you don't check what is there on your laptop. So typically your laptop has a minimum of 4 GB RAM, and sometimes it can go up to 32 GB, but 8 or 16 GB is what typical. 16 GB we are talking about. Here we're talking about 2 MB, a very, very tiny RAM. And then it doesn't have any onboard flash, so you need to attach a flash separately to it to make it a complete device, which we are going to talk about in a moment. And then a lot of interfaces we are talking about. I mean, you can see over here, Ethernet interface and USB and UART, lot of peripheral interfaces that you have. And then you have also some additional peripherals like these interfaces, and then these are peripherals like high-speed ADC, 16-channel ADC you have. And then it also provides a lot of security features over here. So this is the block diagram of, I mean, these are different blocks inside IMX RT1170. And you could see on the right-hand side, the somewhat the same information is put in clean text here. So ARM Cortex M7 processor, 1 gigahertz, it can run up to 1 gigahertz. And some cache features over there. And then you have another processor, M4, which can run 400 megahertz. So how do we configure this? How do we make particular processor do what and specific things and all? That is going to be an application building using these microcontrollers. The other side is design of these microcontrollers. How do I integrate all these devices together, all these blocks together, and make it power efficient, energy efficient, or safety and reliable and all? That is the VLSI chip design side of it. So some of you, when you get into the industry, you could go into the chip design part of it, where you try to integrate and or go inside the blocks. On the other side, you could be a system builder, like I am designing an IoT system for this specific application, and you'll focus on the application side of it. The typical applications where this RT1170 series can go, or the RT series can go, is audio subsystems, customer and healthcare, consumer and healthcare, home building automation, industrial computing, motor control and power conversion. So these are the, in each category, you could see different face recognitions and things like that. IoT gateways and security control systems. You can build various systems using this. So this again, a big domain and industry. How do you build your IoT application for using these microcontrollers? You need to think of hardware, software requirements, optimization requirements, and reliability, a lot of things that we spoke about. As I told you, this device alone does not have the memory, flash memory, and the power management systems and everything. So you have an evaluation kit here called IMX RT1170 evaluation kit. The link I have given it in the top of the slide. So this will give you all the details required. So here, some of the MCU feature directly listed over here, but few others are board features. But this board is what you need to be looking at, because when we ask you to generate a bit file, so you will have to download the SDK for this. We will give you some training material, self-learning material for this. You'll have to target this board, and then software design kit or development kit, SDKs are required for this. So that we will provide. You need to download the SDKs, which will have configuration for all the devices that you see. See the central one, this is actually the microcontroller. Then these are all the peripherals to make build a demo system. It even has this slot for inserting your external flash and so on, and plug-in connectivity for your network and power and adapters and things like that. For all this, you would require a board support package and configurations and things like that. All of that come as a part of SDKs. So these are the different features that this board has. So you don't need to be worrying about each one of these lines, what is written here, but some of these requirements that you need to certainly consider For this hackathon, you need to be mainly focusing on what are the processor capabilities and what are my memory features and available, and how do I map this into it. And if you want to additionally interface a camera and things like that, some of you would have done this using Arduino boards and things like that. It will be very similar, but the device features are much different and much rich here. So those things may have to be slightly considered, but the rest of the things you don't need to be worrying about all of these different features and get bogged down with that. No need to worry. So the implementation is going to be almost pretty straightforward. You'll have to just download the SDK for this kit and use an appropriate software, which I'll talk in a minute, and then you will be done. So consider these requirements while submitting your model in the first phase, because you will not be allowed to change the model once you submit it. So I keep repeating this in every webinar or in every session, that your model should be highly accurate, or accuracy and the model size should be balanced. So you need to consider the image size that you are going to train on, the network of, or the hierarchy of your neural network, and how many layers you have in that. That's an important consideration. With those two, you'll be able to manage the model size. So that's why I'm stressing on these points. So almost, I think we are at the last slide. So what are the software required for deployment? As we spoke, this is a huge system, complex system, and there are so many things to be configured, so many things to be programmed, and so on. You require a good amount of software packages for that. So first, let me talk about the right-hand side. This is the software stack, or the IDE and SDKs that are required to implement to deploy any application you want to build using any of these microcontrollers. You need this. You need this set of tools for editing your C code, for configuring your memory, and configuring some of the peripherals and downloading it onto the device and debug it. You need the right-hand side of the software stack. On the left-hand side is your latest development on, we call it EIQ. So this is your machine learning software development environment. So what does this do is it provides a kind of an environmental platform wherein you can bring your own data, and then we provide you for facilities for annotation and then training the model, inference. And very important, when you use this EIQ platform, it will also tell you what is the estimated memory when you implement it on the microcontroller, NXP microcontroller particularly, this for NXP devices. So you will know upfront what is the RAM required, what is the flash required to deploy your model. That's the biggest advantage you get with when you use EIQ software. But again, it is optional. So you don't want to use this, you train you using any Kaggle or any other, or using any other platform, you bring your train model and you can directly jump in here and deploy it. This is optional, I repeat. And the second part is, okay, I have trained the model. Now I want to do some optimizations using EIQ. You can also do that. Though I wouldn't little bit suggest that to do. Either use EIQ to build your model from scratch, train it, and dump the output and take it to the right-hand side. Or you directly use some other environment, go to the right-hand side for deployment. So in summary, the left-hand side is optional for hackathon. The right-hand side is required only for phase 3. So if you're in phase 1, you don't need to worry about the right-hand side, MCU Expresso. You can optionally use only EIQ. So which I have clearly put it in red and highlight and all of that. So these are your software requirements. So with that, we come to the end of this session. So in summary, we spoke about what is cloud, what is edge computing, what are the differences, what are the requirements, and particularly for edge computation, what requirements, what challenges you have. We spoke about microcontrollers, what is inside it, and then we spoke specifically about what are the challenges with microcontrollers, and then we spoke about an introduction of NXP MCU portfolio, and then we specifically talk about RT1170 device, what are its features, and then we spoke about development board. Then we spoke about deployment of the hackathon problem onto these devices, which are required for phase 3 only. So with that, we open for Q&A. Thank you.
Thank you, sir. Thank you for that wonderful session. Students, we are open for the Q&A.
Yeah.
You can put your questions in the chat box. So we already have one question.
Yes,
When
go ahead.
deploying CNN-based defect classifier on NXP ARM Edge device using EIQ, what best practice do you can recommend to minimize post quantization accuracy loss while keeping latency and memory within age constraints?
Okay, so when deploying CN-based defect classification NXP ARM edge devices using EIQ, too many questions in that. Okay, what best practice do you recommend to minimize post-quantization accuracy loss while keeping latency and memory within edge constraints? Okay, so this is quite a deep question which will require a lot of discussions. I don't have ready-made upfront answers to it. You could probably search on the web and look at answers. But specifically, when you use EIQ, I can answer that you can do multiple experiments with EIQ. You can play around. Okay, choose this kind of an optimization, choose this kind of this many number of loops and this many number of iterations and all. You can do multiple experimentations, and EIQ platform will give you a nice picture of, okay, if you choose this, this is your going to be memory, this is going to be RAM requirements, and this is going to be flash requirements. It will give a comparison of that. That's the biggest advantage of using EIQ. But if you use other platforms, there are similar things. The time is very short to explain. Probably I need to give you some slides and all to explain how to do quantization and all. Frankly, I'm not an expert in quantization accuracy and all. You need to do some experimentation and all.
I hope your sir answers your question. Any next questions?
Oh, only one question. Okay, what should be our approach to train the model? Should we use supervised, unsupervised, partial supervised? Others, okay. Others, this is a very preliminary, very basic question. Because we spoke about this in the last webinar, it is a supervised learning. Unsupervised cannot be done here. Very difficult to do unsupervised learning here. Because if you simply give those images and do an unsupervised learning, I don't know how you, if you know the method to do unsupervised learning for the images. I know how to do that though. It's typically done using VGG16 algorithm where you throw all the images onto the VGG16 algorithm and ask it to classify, you cluster them. It can do, but that is not recommended because it will group based on similar images and so on. So both unsupervised and partially supervised model is discouraged here. It is not that it cannot be done, but this is not the right thing to do. Go for supervised learning, which we spoke specifically in the last webinar.
You can raise your
Wafer
hand
maps
and
allowed. Okay, we clarified this several times in the WhatsApp group also. I think Saurabh posted this. Wafer map images are not allowed because we have given a clear guidelines when we put the kickoff session and the presentation, right? And the sample images that we have attached to the hackathon website is those are the only type of images that you can use, which are SEM images or other kind of images which are taken on the dice. Go to the transistor level. Wafer images are those round on the wafer. You see where the defects are concentrated. There is a data set available for that, and we are not going to accept if you submit that. So wafer map images are not allowed for this hackathon. Any other questions, please? Okay, the model have to just to detect or classify as well. Okay. So again, we spoke about this in the last. What do you mean by just detect or classify? Okay, let me also answer that. So if the if that image has a defect of various kinds, we are asking you to classify that into what kind of a defect it is. So for this purpose, it is good to select one defect per image. Select those kind of images. One image has VR defect. One image has only the bridge defect. So we want to focus for now on those parts. Probably in the next year, we may think of doing another hackathon wherein we will ask you to do object detection, wherein in one image you have the bridge as well as a crack. So we want you to mark where the crack is. We want you to mark where the bridge is. So that will be a different exercise. Today, we are good if you submit a model which can classify a clean image. There are no defects in it. The other image, okay, I see a bridge defect. Though there is an open defect, even if it classifies as a bridge defect, because the defect is there in that image, we are good with it. So we need classification to that extent. So we see another question. AI-generated images were used only to augment underrepresented defect classes and improve class balance during early prototyping. Model evaluation and validation were primarily based on real inspection images. As we told you, we want you to experiment as much as possible here. We want you to come out with all your innovative things and also test some of your generative AI models. What kind of images that they generate. We are going to take a look at what images you have generated and we will do an assessment on that. So because this data is not fully available and fully accessible, so we have left it a bit open for exploration and apply your creative thinking on it. If you understand what a defect is, even you should know how to prompt and your GPT, ChatGPT systems. You need to know how to prompt it. Otherwise, it will just give you some crack image and things like that. So we're fine with you to experiment, but we'll examine the images that you generated and then we'll see. Yeah, some images from IEEE research papers like this one can be used as training in data set. This is correct. Will this be boss one? What you posted is the one correct one. Yes. This is what we want you to use. Yeah. So next one, other shots. So we do not have to mark where the defect is. So we also said this. This is going to be a little bit cumbersome because you need to do a lot of annotations and things like that. We did not have enough time for that. So hence, we did not give you object detection problem. We gave you only a classification problem for now. So you don't need to mark where the defect is in this part of hackathon. How much size of the model do you recommend? I want you to give me the model as small as 10 KB. Is that possible? So you please look at the microcontroller features and what require what. I think I have covered quite an amount of content to give you an idea of what kind of memory you should be looking at. And again, someone is asking less than 10 MB is fine. So this is going to be an open contest, and someone gives me 9 MB with a good accuracy. 10 MB model will score low, and 9 MB model will be fine. Will score high. So it's going to be a competition. So you try to limit your model as small as possible while maintaining good accuracy. I don't want to specify a number. So this is something I would also want you to look at the EVK board 1170. Now that we have defined what board you must be targeting, look at what its memory requirements are and then accordingly work on it. The minimum requirement is your model should fit into that device. And the actual recommended requirement is that fitting also should be so small that I have space for doing something else on that device. Other questions, please? Looks like that's the last question.
Yeah, seems to be.
I think we have left with 4 more days for the first phase 1 submission, right, Saurabh?
Yes.
Yeah.
So if you have any more questions, please clarify because this is the last session before the end of the phase 1.
Yeah. In public, there are semi-majors with a different electrical pattern. Okay, what is the question? This is statement.
I guess he meant to say that available images are with different electric patterns.
So what is the question?
Yeah. Others, yeah, you can, if you want, you can raise your hand. I can unmute you, and then you can ask
Yeah.
a clarified question.
We have 5 more minutes. Yeah. Okay, someone posted a question. This is Bala from, okay, we would like to understand the major challenges involved in deploying AI models on edge device with semiconductor manufacturing environment. In addition to model architecture and model size, are there any other critical configurations or system level considerations that need to be addressed for real world industrial deployment? Yeah, good question from Bala. Yes, there will be plenty of other challenges. For now, we don't want you to worry about any of those challenges. Maybe if you go to phase 3, so innovatively you bring up, do some more research and work on that, and then present your findings and recommendations in phase 3 session. But for now, we would want you to consider only those aspects: accuracy and model size. Focus on them. Otherwise, it's too big a hackathon exercise you cannot complete in this time. I hope that's clear, Bala. Okay, so Shaurya. Okay, so the kit is provided on phase 3. Ideally, we would want to provide a kit, but we may not reach the stage because 10 kits and all we are not able to find in the short span of time. What we will ask you to do is, we told you in the kickoff session itself, this is no hardware download will be required. You will reach till the download point and then stop there. When you go to the 10XP MCU Expresso software, so once you prepare all the design and target this 1170 board and do all the configuration, there's something like compile and generate the bit file. If that step is successful, then your phase 3 exercise completes. You don't need to connect it and download. Thanks for asking this question. Many had this question. So we're not going to give you any boards as such, but we'll give you all the software. Again, all the software is freely available. You'll have to just do a registration. And some of the links that I have provided you, they are register and access only links. So you need to register and then access that. So please do that. We are using ChatGPT generated images for training our model. The model is learning and training properly, but it is overfitting and not performing well on new or unseen defect types. What can we do to improve generalization and reduce overfitting in this case? Okay, then this is something you need to solve for yourself. Then I'm answering the question and then giving you hints, and then others will say this is unfair. If you ask me separately on an email, I will not answer this question. So you decide how do you solve this problem. Ask your mentor. This is actually the challenge of the hackathon. Mithun. Okay. Any other questions? And for the current Bala, and for the current stage of this hackathon, is it mandated to implement and validate a solution directly on an NXP processor? No. Or is it proof of concept using development platforms accepted before migration to NXP Edge? Yes. So you just look at the hackathon posting on the web, right? We have clearly defined your deliverables. I think 1 to 5 or 1 to 6, 1 to 5, something like that is required for phase 1. 6 is for phase 2, 7, 8, 9 is for phase 3. Currently, you focus on phase 1 till you win the contest.
It's quite simple. You have to collect data set, build the data set, submit that with your ML models applied on that. That's accuracy and the model size. This is quite simple ask.
Again, don't look at this recording in this session. Please read the document. We are going to follow the document. You said, sir, on the webinar on 4th of February, you told me, give me data set and accuracy. I submitted this. Where is my evaluation? No, please go through the hackathon document, submit it as per that. We have clearly defined what to come.
Yeah.
Okay, we are at the end of the hour. So thank you who had a real clarity. Okay, thanks, Meenakshi. Yeah. Okay.
You,
So with that, we wish you all the best, and please rush and submit. Keep all these factors in mind. Saurabh, over to you. Any closing remarks? Thanks.
so, so this was the last session before the phase one ends. So uh, as you guys know, like the 8th Feb is the last date for you to submit your idea for the phase one. Please do check the website and the PPTs share with you. Also, other details and descriptions are given on over the WhatsApp group as well. Go through the recordings which are shared of previous webinar and these orientation sessions for if you require any clarity. If you have any questions, we have already shared our email IDs with you. Also, Malikarjun sir's email ID is there. For technical questions, please reach out to him and keep my email IDs in the CC so we can keep that track of that. If you have any general questions, please reach out to only me or support@ICC.com. Yeah. Um, Thank you. And again, on behalf of IESA, NXP Semiconductors, and FOC, I extend our sincere thanks to Malikarjun sir and all the partners and all the experts who want to come in and will be participating in this hackathon, making this hackathon a grand success. Also to the participants, thank you for registering. So I'd like to say like we almost have 791 teams registered for this hackathon. And by the 8th of February, we may cross 800 as well. So the competition is quite huge. And also there is an opportunity because as this problem state is quite new, when the NXP is working on this and there is a good opportunity to you guys to come up with an innovative solution. This may also lead you to get an opportunity for an internship or maybe also job with any company. This can you can show this as a uh, good project for your engineering or any other thing. So please take this hackathon quite seriously. Do more experiments. Uh, so please try to attend at least. I'll say even if you're not able to come up with a good solution, but try to attend creating the images, running the ML models, let me say, and keep learning, keep innovating, and build the solution. And this definitely will strengthen our Indian semiconductor ecosystem. Keep on going through the news. The news are quite hot right now regarding the semiconductor sector. Quite
It's
exciting.
hot. It's there everywhere
Yeah.
in India. A lot of opportunities.
Yes. No problem.
Going forward.
Thank you. Thank you. Thank you, sir. Have a great evening.
Thank you all for attending. Bye for now.
Thank you all. Thank you.